As Mitra said, my name is Mike Mesh. I'm with AT&T. I work in the mobility transport group as a design engineer. The product that we're presenting on today is a product that we coined a phrase or named as a CAS, a Converged Access Switch. Before I get into the slides, I do want to caveat and say one thing is that the slides we've put together today are meant as a very high level, more of a requirements level presentation. The objective is to solicit collaboration among the community, develop the requirements, complete the design specification, and then come back in the June timeframe and actually present a more detailed specification that a supplier could build to through partnership through this community. So what is a CAS? A CAS is a transport aggregation switch. Our thoughts is that this device would mix together different types of traffic from CPRI, eCPRI, Ethernet such as enterprise services, and then transport that through a Ethernet packet-based aggregation system. The objective of this device, or excuse me, I should say requirement for this device, is that it's standards-based, ORAN, XRAN compliant, so that we can have interoperability among different providers. We also want this box to be very flexible, and we achieve that flexibility through modularity. Modularity to support different types of traffic, as well as different vendor implementations for legacy CPRI-based systems. Another very strong requirement that you'll see is the low latency. Because this is supporting 5G transport, we've got some pretty stringent timing requirements as far as latency. Lastly, this box should be SDN controlled, white box, and it should support any NOS that a supplier would want to, or carrier would want to place on this box. Some very high level requirements, starting off first off with ROE. Now, there are several different flavors of ROE. There's structure agnostic, there's structure aware. With each of those steps, there's various benefits, but for the benefits, those benefits being reduced front haul bandwidth, you pay the price for that reduction by increased complexity. So it requires you to have vendor specific, for the structure aware, vendor specifics on the CPRI structures to be able to transform that CPRI interface into frames for transport. Another point about the ROE is you see here a deployment. We would have two of these CAS boxes. One CAS deployed at a tower location, a mated CAS at a hub location. So as the CPRI would come from an LTE radio, it would go through the CAS and then would use the ROE mapper to convert that CPRI into frames for Ethernet transport across our front haul network. And then when it reaches the hub site, you'd have to have an ROE demapper to then convert that back to the exact same CPRI structure that the BBU would be expecting. The next requirement is TSN, time-sensitive networking, specifically the 802.1cm preemption. TSN is required. I know this is a very debatable within the industry. For links, depending on your packet size. So if you have a packet of less than 2K, then on links greater than 10 megabits, or excuse me, 10 gig, you probably don't need TSN. If you have a larger packet size, that minimum threshold goes up. Even with like a 9K packet, beyond 25 gig or link speeds greater than 25 gig, the TSN becomes obsolete. Now, latency. What I've got described here is a total round-trip latency of 125 microseconds. Now, that is from the egress of the radio head through the network, so it's got to pass through 2 of these CAS devices, as I talked about, to the BBU and back. Now, that 125 does not include the processing on the BBU itself. Now, if you do the math, you'll say, well, for 10 kilometer, you're looking at about 100 microseconds just for transport time. And again, this is round trip, so you take that remaining 25 microseconds and you divide that by 4, you're looking about 6 microseconds per CAS to perform that operation. Now, which operations am I talking about? Well, I'll talk about the lo-fi feature here in just a minute. I do want to just point out that this 125 microseconds, does exclude the lo-fi feature that would be housed in the CAS. So we'll talk about that in a minute. Next major requirement is 1588 synchronization. We'll talk about, on the next slide, multiple form factors and deployment locations for the CAS. So depending on where this CAS is deployed, whether it's deployed at the tower, we will be looking for boundary clock requirement. If it's deployed at the hub location, then it's an EDGE Grandmaster requirement. Next, switching and routing, very similar to the previous requirement that said, the requirement varies based on deployment location. Total switching throughput would vary as well. It could vary from 200 up to 800 a terabyte, depending on those locations. The other point I want to make out with the switching routing is a layer 3 requirement. And I know that there's also been some debate as far as, do you need just VLAN tagging? Do you need full layer 3 support? Our thought is we would want to see full layer 3 functionality. As I talked about on the previous slide, we're not only transporting CPRI and eCPRI from the towers, we're also hoping to be able to transport business services, Ethernet services over this device as well. So that, in our mind, is driving that requirement into full layer 3 capability. Additionally, we talked about the NOS. We want this to be an open white box, support any version of NOS of the supplier's choice. The last requirement I want to talk about on this slide is what we call lo-fi. So what lo-fi does is, if you look at a legacy BBU and you take the lowest layer, the PHY layer, and you split that in half, and then take that lowest layer of the PHY and move it out to the tower. Very similar to what 5G radios have done today. So a 5G radio has already split that PHY layer and is inclusive of the lo-fi. So like ROE, lo-fi would provide us front haul bandwidth reduction. As I mentioned on the various layers of ROE, lo-fi is the next layer. The complexity goes up, but also the benefit goes up on reduction of bandwidth. Now, bandwidth reduction is great, but one of the other benefits that we see of doing the lo-fi, it allows us to consolidate, unify our BBU architecture at our hubbing sites. This will allow us to take a 5G BBU and be able to terminate a LTE radio. So in other words, instead of having here at our hub site having a 5G BBU as well as a 4G BBU, we simply have that unified single 5G DU in this case, and then the CAS would perform that conversion from CPRI into eCPRI for ingestion into the DU. Now, deployment locations for the CAS. I've drawn 2 separate examples here. So in this top example with the LTE, we have the lo-fi at the tower. So it goes through, takes that CPRI, converts it to eCPRI, and performs the transport. Now when it gets back to the hub location, that has already been converted, so it does not need to do a second lo-fi conversion. It's not like the ROE where you got to put it back into its original format. In this case, we don't want that. We want to keep it as eCPRI. In the bottom case, an example where we have not yet upgraded that tower, do not have lo-fi at that tower location, we go through the ROE mapper, we send that over to the hub by an Ethernet interface. Now once you get to the hub site, we would have to take that Ethernet message, go back through ROE demapper, put it back into CPRI, then through the lo-fi to convert it to eCPRI for ingestion into the 5G BBU. Easy, right? All right. So we talked about different locations, different requirements based on where the device is located. And so we envision at least two form factors. We have Pico sites today where very little space at the towers. We want a very small form factor device, outdoor hardened IP65 type device that we can deploy at a pole site. It would also terminate both CPRI and eCPRI. Now, even though I don't have it drawn on this particular diagram, we also foresee the need for it being able to support Ethernet services in case we want to use that particular site as an IAB site where surrounding Pico sites would connect to that site as a drain site out back to the hub. The second form factor that we're considering is a 1RU rack mount device. This device could be deployed not only at the tower site, but at the hub site as well. Now, from the tower side, the cabinets that we use for deployment, there's not much depth. And so there would be a restriction for this device to be about a 300 millimeter depth, 1RU, 2RU. Now, I also mentioned flexibility was one of our requirements. And so we envision this device to be able to support the inclusion of different processors from various suppliers to support their version of CPRI. As I told you, the more complex you go, the more benefit you get from, in this case, lo-fi, the more complex. We'll go into that a little bit more in the following slides. The connection between the tower and the hub site. We pay a lot of money for fiber connectivity out of network. We lease lines. And so one of the objectives of this product is that we have a single fiber connection connecting the tower site and our hub site. Now, majority of our towers, that's not a problem. We can have a single 100 gig connection for transport. However, there are some sites that would surpass that 100 gig capability. So in those cases, what we're proposing is that we have passive WDM filters on both sides that we could terminate in multiple connections from the tower so that we could increase that bandwidth from 100 gig to potentially 400 gig by using multiple lambdas. So let's talk about a little bit more about the CAS at the hub site. So this 1RU device, to gain that capacity at the hub site, we would instantiate multiple versions. Depending on how large that hub could be, it could range into the hundreds of CAS devices co-located within this hub. Subtended off the CAS, we would be the BBUs, 5G BBUs, and eventually the DUs. In AT&T's case, we then would connect those DUs back to what we call a SIAD or cell site router, which is also an OCP design, by the way. We talked about the device being able to support CPRI, eCPRI, and Ethernet. So that Ethernet could be backhaul traffic. So for example, at this tower could have a BBU co-located at the tower. It could then provide an Ethernet interface into the CAS for that backhaul. Front haul traffic coming off the towers, as well as if you deploy this device at a macro or a micro site on top of a large office complex, we would foresee terminating those Ethernet services into this device for transport back to the hub. All right. So a little more details on the varying form factors. So starting off with the Pico CAS, an example I was showing before, I showed it mounted onto a pole. Within our network, we also want to support the ability to do a strand mount device as well. Now, I mentioned 2 form factors, but there's actually could be more. So AT&T's requirements for pole mount versus strand mount, the power requirements are different. We have AC in one location, DC in another. Because this is a small form factor hardened device, we would envision that being 2 different SKUs for these different power requirements. Now with respect to ports, on the smaller device, we've specified one N&I port of 100 gig, and then we've also listed out 8 ports for the client side or radio side. Now we did split those to help specify the requirements. So we're saying we need at least 6 ports that initially would be used for CPRI. So we said it must support 10 gig. But as 5G evolves and we start deploying, densifying our network, we would envision that we would deploy more in our base radios and would require more CPRI interfaces. So these 6 ports must support 10 to 25 gig CPRI and eCPRI. Additionally, 2 ports would be dedicated strictly to eCPRI. We did the same type approach on the larger unit that we call the CAS, the 1RU device, with 18 ports that would be the combo ports for CPRI and eCPRI. 6 would be exclusively CPRI, and we would specify 400 gig uplinks back to the hub. And I say back to the hub, this device, our plan is to have the same SKU that could be deployed on both ends. So not only would it be deployed at the tower, the hub, it'd also be deployed at the tower. Now, with respect to environmentals, because the Pico CAS is deployed at a tower location, we would require an IP65 compliant device, the NEBS class 4. The rack mount would be deployed, as I mentioned, in something like a Purcell Flex 16 cabinet, and so therefore it would be an IP54 requirement, which is the NEBS class 2. With respect to the features we talked about on the previous page, lo-fi, now I did put optional here. It is highly desired that we have the lo-fi capability at all of our sites, at the Pico as well as the macro and micro sites. Some of the feedback that we received from some of the manufacturer saying it may be a challenge to get the number of devices, ASICs versus FPGA, into that small form factor and still be under our max power requirement. So we said optional but desired. For the CAS unit itself, required. Now, as I mentioned, lo-fi, the complexity on lo-fi can be quite high, and so we're willing to discuss some development scenarios where we initially would deploy lo-fi ready hardware into the network and then come back at a later phase once that lo-fi IP was developed and add on that additional lo-fi feature. As mentioned in the very beginning, the objective of this presentation is to list out requirements. And so on this block diagram, I'm not showing any device names, any suppliers, just very high-level concept type block diagrams. On the far left-hand side, the first option we've shown is an ASIC device. Now, because of the nature of an ASIC, we do not anticipate an ASIC supporting the lo-fi feature because that lo-fi feature will be specific to a particular RAN supplier. It could be specific to a radio or even frequency. So with the amount of change for lo-fi and the varying nature, lo-fi, if ever, would ever be supported on an ASIC. Now there are some potential sites where we see some benefit of having just ROE and the other features without lo-fi, so we went ahead and listed that as an option. The second option is a pure FPGA type solution that would support all of our requirements from ROE, lo-fi, as well as supporting layer 2, layer 3. As I mentioned, our goal is to have complete layer 3 functionality. That may be a challenge depending on the size of the device, the amount of traffic, the requirements for 1 terabyte, so forth. So the third option that we detailed is what we're calling a hybrid approach. And in this hybrid approach, we would have an ASIC as well as an FPGA. Now, how the functionality is split between those devices, whether the ASIC is just supporting layer 2, layer 3, or whether that ASIC has the features like the ROE 1588, TSN, we did not detail that. That's something that we still need to work with the suppliers, the community, to design how those features would be allocated across these processors. Now, the three options I'm showing here is for the rack mount device. For the pole mount, for the Pico, we did eliminate that option of having a hybrid. As I mentioned from the matrix diagram, that having those multiple devices, having that hybrid solution on a small Pico device may be challenging. So we left that off of this slide, but did detail a solution that could use an ASIC, again without the lo-fi feature, and then having a pure FPGA solution that would have to meet all of the requirements. All right, so call to action. So I indicated this was a very high-level presentation. It's an introductory to share with you what our thoughts are, what we see as requirements. Again, they're very high level. We want to enlist additional help, collaboration. We want to partner with several different suppliers as well as RAN suppliers to develop these requirements and put together a specification. Our goal is for the next OCP session, which is coming up in June, that we have all these requirements and designs ironed out, documented, and present to the OCP community. So I'd like to encourage you, if you have questions, if you have thoughts, we have the mailing list. I have my work email here. Join the collaboration effort and provide us feedback. All right, questions? Yes?
When you say when you say the full layer 3 capability, can you elaborate a little bit? For example, does it include the segment routing, EVPN, or even upcoming like enhanced VPN, stuff like that?
So that's probably one of the biggest questions I get is, what are your layer 3 requirements? We don't have all the answers yet. We're still documenting various use cases. Because of the fact that we're wanting to be able to offer Ethernet services through this device as well, as I mentioned, is what's driving us to say we need layer 3. But when exact details, yes, we think we need MPLS, yes, we think we need segment routing, The justification and the use cases behind those have not yet been documented. But those are one of our first efforts that we want to kick off is get those layer 3 requirements, because I think that's going to drive the selection of the devices within the box.
Yeah, thank you.
Mm-hmm. Yes?
What is the timeline expected to be deployed?
Timeline is the question. We would like to see prototype devices by third quarter of this year. And the actual deployment timeframes, we would like to see something by a year from now. Yes?
Follow on the first question. I think in one picture you show after your box, and then you go to the BBU or DU, and then go to the cell site gateway, which is going to run like layer 3 zones. So you have a layer 3 box, layer 3 feature on your box, and then you have another cell site gateway with
Yes.
layer 3. So, you know, it's kind of redundancy or whatever.
So that is correct. I just acknowledge that for now, say there's still some design efforts that are underway. So yes, I hear your point. So I'll table that question till we come back with more detail. How's that? All right? All right. Thank you.